A stone dropped in a still pond sends out a circular ripple whose radius increases at a constant rate of 3 feet per second. How fast is the area enclosed by the ripple increasing at the end of 10 seconds where the radius equals 30 feet? So the first thing I like to do with these problems is find a find and a given. So what am I given? So notice how they told me with respect to the radius increases at a constant rate of 3 feet per second. So that will be my dr dt. So given dr dt, they want me to find dA dt at the instant where the time is equal to 10 seconds and the radius is equal to 30 feet. Right, now this dr dt is just 3 feet per second, right? And again, the radius increases at a constant rate of 3 feet per second. So that will be my dr dt. Again, how fast is the area enclosed? So now we know that, and maybe we should draw a picture here. We have a stone that is dropping and it's forming a circular ripple, right? So we know the area now. The area for circle is pi r squared. So we're going to take the derivative of this formula and just plug in our values to get our answer. Again, they're asking how fast is the area changing, right? So now they're asking for dA dt. So let's start a process. So the derivative of A is just dA dt with respect to time. That is going to equal 2 pi r dr dt, because we've just taken the derivative of the r, all right? And the issue is that whatever variable you take the derivative of, that will be d whatever with respect to time, all right? So now that we have a formula, we're solving for dA dt, so everything is already on one side, so we're just going to plug in our r. In this case, the time doesn't matter, right? So dA dt will be 2 pi, r is 30 feet, all right? And then dr dt is just 3 feet per second. 3 feet per second, all right? And we just multiply these, all right? So again, dA respect to time, well, 2 times 30 is just 60. 30 times 3 is 180. So this will be 180 pi feet squared per second. And notice how the unit should make sense. We're talking about area, we talk about square. When we talk about volume, we talk about cubic units, right? So make sure your stuff makes sense. Let's look at another one. So here this problem says a ladder 5 meters long is leaning against a wall. If the lower end of the ladder slides away, right, from the wall at a rate of 0.5 meters per second, how quickly is the top of the ladder moving down the wall when the base of the ladder is 2 meters from the wall? So again, maybe we should draw a picture here, right? So we have this triangle here, all right? And we have a ladder basically leaning up against this wall, right? So the ladder is 5 meters long. So my D right here will be 5 meters. Or, you know, you could call it, because usually we're going to use a Pythagorean theorem in this one. So it's usually a squared plus b squared is equal to c squared. But I kind of always label my c squared, right, as my D. So however you want to choose it, right? So my D here will be 5 meters long, right? So if the lower end of the ladder slides away, which means that this is going, it's going this way, right? So our X value is kind of increasing. So if that is going away, then our Y value is kind of decreasing, right? So again, if the lower end of the ladder slides away from the wall at a rate of 0.5 meters per second, that will be your dx dt, because we're talking about a rate as the ladder slides away from this axis here. So our dx dt given dx dt, and that will be 0.5 meters per second. All right. Find, well, what they're asking us to find, how quickly is the top of the ladder moving down? So now they're asking us to, basically they're asking us to find dy dt, right? So find dy dt, right? When the base start moving down the wall, when the base of the ladder is 2 meters long. So when x is 2 meters, right? So we know d is 5 meters, or x will be 2 meters. Again, because when the base of the ladder is 2 meters long, we're talking about the base here. So this will be 2 meters, that's our 5. We don't really know what y is equal to. So in this case, the Pythagorean theorem, a squared plus b squared is equal to c squared, but I'm going to use x times y. So I'm going to use this as x squared plus y squared is equal to d squared. And this is the same thing as the Pythagorean theorem, just different variables. So I hope I don't confuse you. Now this is a right triangle. So now we're going to take the derivative and kind of plug in the values. So 2x dx with respect to time plus 2y dy with respect to time, and that's just going to equal 2d dd with respect to time. All right. Now here's the thing with these ladder problems you got to catch. Everything else is changing. The length of this ladder is not changing at all. Notice we're going down, we're increasing over here. The length of this ladder is not changing at all. And so the good thing you know about the derivative of this is actually 0. So dd dt is 0. And 2 times 0 is just 0. So this will automatically cancel, right? So now we're solving for dy dt. So we could just subtract this on the other side and we get 2y dy dt is equal to negative 2x dx dt. All right, now we could just divide by 2 on both sides and these will cancel out. All right, these will cancel out again. All right, so now we could divide by y on both sides. And once we divide by y on both sides, we get something like this. Or dy dt will be isolated. And this will be now x over y dx dt. Right? That will be x over y dx dt. Again, all we do now is just plug in our values. So dy dt will be, or x value is 2 meters, or dx dt is right here, so 0.5 meters per second. All right, now we don't know a y, right? So here's what we could do. We could set up a Pythagorean theorem triangle, a right triangle rather, right, where this is 5 meters, x is 2, all right, and according to c squared, according to a squared plus b squared plus c squared, your, I guess I could call this b, your b squared will be c, the square root of 5 squared minus 2 squared, and that is just the square root of 21. You could do that in your calculator, right? So y here will be the square root of 21, all right? So dy dt will just be 1 over the square root of 21 meters per second. All right, and that should be your answer for this problem. All right, now, and you notice I dropped the negative sign here because, again, it's hopeful to think the ladder is kind of increasing, and so it's not decreasing, and so a negative wouldn't do us any good here. Let's look at another one. So I have this problem here where it says a rocket is launched vertically, is trapped by a radar station that is on the ground 5 miles from the launch pad. How fast is a rocket rising when it is 4 miles high and its distance from the radio station is increasing at a rate of 200 miles per minute. All right. So again, this is a triangle problem. All right, and you could imagine this being our launch pad. This is where a rocket is rising vertically. Can't draw a rocket here, but rocket is rising vertically, right? So a rocket that is on the ground 5 miles from the launch pad. So our X will be 5 miles here, right? How fast is the rocket rising when it is 4 miles high? So it tells the rocket is 4 miles high. So again, our Y here will be 4 miles, right? Now, its distance from the radar station is increasing at a rate of 200 miles per minute. So our DD, with respect to time, will be 200 miles per minute. Again, x squared plus y squared is equal to d squared. We're going to set up our formula. Take the derivative 2x dx dt plus 2y dy dt is equal to 2d dd dt. Now, you could imagine the derivative of this doesn't change at all. The derivative of this does not change one bit. And so the derivative with respect to x, dx dt is 0. It doesn't change because we're at a launch pad. The rocket is rising. We're still 5 miles away. This doesn't change. The derivative of this doesn't change at all. Right? So really, we're solving for, let's see what the problem says. How fast is the rocket rising? So, right? So the rocket is rising on the y-axis. So we're going to find dy dt. All right? So we could divide by 2 on both sides and get these 2 to cancel out. And we could also divide by y on both sides, and we get our final answer to be something like this. dy dt is equal to d divided by y, dd dt, right? And now we're just plugging our values. Again, dy dt, they're asking us how the rocket or the vertical axis is changing, right? Good news is that we have our y, which is 4 miles. Or dd dt is just 2,000 miles per minute, right? We do not have our d, right? And so we got to use a triangle to set it up, right? So right triangle, so something like this. We have a right triangle. Sorry, my triangles are horrible, right? So this is 4. This is 5, right? And again, using your rule here, the rule says c squared is going to equal the square root of 5 squared plus 4 squared, right? And that is just the square root of 41, right? So y here is just the square root of 41, right? Good thing to know, we could cancel these out, and this will be 500. 4 times 500 is 2,000, right? And so your final answer, dy dt, is going to be 500 square root of 41 miles per minute, right? And that will be your final answer as to how the rocket rises.